Good. So in this video, we'll look at some of the reactions of monosaccharides, particularly the formation of cyclic monosaccharides through hemiacetal formation. So the first one that we'll look at real quick is the reduction of monosaccharides. And this is used to create alcohol sugars. By converting carbonyl groups, such as the aldehyde or ketone, to hydroxyl groups. For example, the reaction we discussed in the previous video of D-glucose to sorbitol. So the reduction of monosaccharides is good for producing these alcohol sugars, which are oftentimes used as sweeteners. The next reaction we'll look at real quick is oxidation, and there an aldehyde or hydroxyl is converted to a carboxylic acid. And this oxidation reaction is actually taken advantage of in order to detect sugars in solution using what's called Benedict's test. Which is a basic solution, so it's got a pH well above 7 of copper 2 ions and aldehydes so aldoses can reduce that copper 2 to copper 1. And in the process, these aldehydes are converted to carboxylic acid. And so another term for aldoses is a reducing sugar, because that aldehyde can reduce that copper 2 to copper 1. And so reducing sugars are any sugar that tests positive in the Benedict's test. And this test is fairly easy to carry out because those copper 2 ions are blue and the copper 1 ion is brown. And so when the solution changes from blue to brown, we know that there's reducing sugar in the solution. And so we can measure how much sugar is in that solution by measuring the color change from blue to brown. However, there are some ketoses that will test positive as a reducing sugar, even though the carbonyl group of the ketone cannot be oxidized to a carboxylic acid. And one example of that is fructose. So this is D-fructose. Again, it's D because this hydroxyl group points to the right. And we're going to convert this carbonyl to we're going to end up converting this ketone to an aldehyde. That what happens with D-fructose is that in basic solutions, so when there's lots of hydroxide ion in the solution, that this D-fructose will actually convert to either D-glucose or D-mannose. So this would be the D-glucose. Or the D-mannose. So again, these are D sugars. But we've ended up moving this carbonyl from this internal position where it's a ketone to this external position where it's an aldehyde. And so we've converted the fructose to either glucose or mannose depending on the orientation of this hydroxyl group at the C2 position. And because the D-fructose converts to glucose or mannose, it tests positive in Benedict's test because even though fructose itself is not a reducing sugar, both glucose and mannose are. And so these would reduce that copper 2 to copper 1 and change the color from blue to brown. And so the fructose would appear to be a reducing sugar, even though in reality it is not. So the third reaction that we'll discuss, and the most important, is hemiacetal formation. And so a hemiacetal is formed whenever an aldehyde or a ketone reacts with an alcohol. And so we'll draw formaldehyde plus and I'll color code this to hopefully make it a little easier to understand. But formaldehyde plus methanol and so we've added this this green colored hydrogen atom will add to our carbonyl oxygen, and then the OCH3 from the methanol will add to our carbonyl carbon, and we'll wind up with this carbon that has both an OH and an ether attached. So let me So a hydroxyl plus an ether. And that makes this whole group is called a hemiacetal. And so why are hemiacetals important for sugar chemistry? Well, recall that a sugar has a carbonyl, either an aldehyde or a ketone, and alcohol groups. And so a sugar can react with itself to form a cyclic hemiacetal. And so we'll draw out how that works. Oh, and I should point out, hemiacetal formation requires acidic conditions. Just for this, let me draw that proton on the other side. Then 1, 2, 3, 4. Then if we take this hydroxyl here, then we have, oh, by the way, this is D-glucose again. But if we put D-glucose into solution, then it will enter an equilibrium between this linear open form and in this cyclic form. And I'll draw that bond there to show that we've formed a circle between this oxygen and this carbon. And the other way to draw this is with a hexagon. And we typically put that this oxygen into this position of the hexagon. And then to draw glucose, we need to remember the positions of these hydroxyls. And so this is the cyclic glucose, and this is the linear glucose. And anytime we have a linear sugar in solution, then it will enter into an equilibrium between the linear form and this cyclic form. Now this hemiacetal can actually form in two different ways. And those two different ways produce two slightly different structures. So if the carbonyl group of our linear glucose points down, then when this oxygen here attacks that carbon to form the hemiacetal, then that hydroxyl group, let me color code that so it stands out a little better. this red oxygen from the carbonyl will form a hydroxyl group that also points down. But if this carbonyl points up, and I'll draw what that looks like. I should color code this one too. If that carbonyl points up when the ring closes, then that hydroxyl group that it forms will also point up. And we have names for these two structures. That if we look at this carbon here, and how it points up above the ring, and it comes across and it comes down. And so if it has this sort of shape where that carbon points up and this hydroxyl points down, we call that the alpha anomer. Whereas if the hydroxyl points up in the same direction of this carbon, then it's the beta anomer. And the way that I remember it is that I think that this shape here is kind of boat-shaped. And so I remember beta boat. And the alpha anomer is not boat-shaped. And so it's easier for me to remember beta boat and recall that the beta anomer must be boat-shaped, whereas the alpha anomer isn't. So anyway, these anomers, because they're in equilibrium, and we always have rotation around this single bond, and so that carbonyl can point up, it can point down, it can point up, it can point down, and so we end up with an equilibrium between alpha and beta anomers, that they interconvert, that the alpha anomer will convert back to a linear form, that carbonyl will rotate from pointing down to up, and then will recyclize, and we'll get the beta anomer. And the beta anomer will go through the reverse to get the alpha anomer. And so this whole thing exists in an equilibrium, where the alpha anomer converts to the beta anomer and back and forth. And we call that interconversion mutarotation. And so that just refers to the conversion between alpha and beta anomers. And so now that we've discussed how we can get cyclic monosaccharides, there's another classification scheme, another set of names we have to remember. And that's because these hemiacetals can form with different ring sizes. That if we have a 5-membered ring, well, this looks similar to a compound called furan. If we have a 6-membered ring, well, then it looks similar to a compound called pyran. And so a 5-membered cyclic sugar will be called a furanose. And a six-membered cyclic sugar will be called a pyranose. And so we'll end up attaching the words furanose and pyranose to our sugar names in order to classify them as being a 5-membered ring or a 6-membered ring. And we'll show some examples of those here in a bit. But another thing is, when we draw D sugars, so I'll draw the alpha anomer of glucose. So remember, this is the alpha anomer. Because it has this sort of pattern to it. That hydroxyl points in the opposite direction of this carbon. The other thing to remember is this is a D glucose. How do we know that it's D when we're not looking at the linear Fisher projection? Because this carbon points up. And on all the D sugars, we'll draw that carbon pointing up. That if this were an L glucose, let me label this one first. D, in fact, let's use the full name, alpha D glucopyranose. And so these different parts of the name tell us different things about the molecule. Like the alpha tells us that this hydroxyl points down. The D tells us this is a D glucose, that this carbon with its hydroxyl points up. Gluco tells us it will be a glucose, and so that tells us the pattern that these hydroxyls need to point to make it glucose. And pyranose tells us that it's a 6-membered ring. 1, 2, 3, 4, 5, 6. So yes, we can find out different things about the structure from the name. Now, if I wanted to draw in L glucose, then I'd have to reverse the orientation on everything. Including this carbon here. So it would come down. It's a little hard to draw because I have to draw it behind the ring, but it would point down and away instead of up and away. And so this would be alpha L glucopyranose. This is the D, that's the L. We'll almost never see an L because L doesn't occur naturally. But anyway, we'll finish up with some examples to help make us more familiar with the naming system: pyranose and furanose, and alpha and beta anomers. So these are both examples of galactose, cyclic galactose, We have a 6-membered ring, so there'll be a galactopyranose, This carbon atom here points up on both molecules, so they're both D-galactopyranose. And in this example, this hydroxyl points down. In the second example, the hydroxyl points up. And so that's beta. This is alpha. And so it would be alpha D-galactopyranose or beta D-galactopyranose, depending on which one we're looking at. So the next example this is a ribose, and it's a 5-membered ring in each case, and so it is ribofuranose. We have this carbon here on the right pointing up in both cases, so they are both D-ribofuranose. This hydroxyl here points down, this hydroxyl here points up. So this is the alpha anomer, this is the beta anomer. And so it's either alpha or beta D-ribofuranose. Now we'll look at an amino sugar, which is a modified sugar. Now, this is a glucose, but we have this amino group, and so it's glucosamine, and so the name becomes glucosaminopyranose, and again, it's pyranose because it's a 6-membered ring. These carbons point up, so it's D-glucosaminopyranose. Then again, this hydroxyl points down, making this the alpha anomer. This hydroxyl points up, making this the beta anomer. So it's alpha and beta D-glucosaminopyranose. Now we'll look at a deoxy sugar. And so in this deoxy sugar, we have replaced the hydroxyl at this position with a hydrogen atom. And so This is a deoxyribose. It's a 5-membered ring. So it is, well, actually, we have to also look at the position. This would be carbon atom 1, 2, 3, 4, 5. So this is a 2 deoxyribofuranose. 1, 2, 3, 4, 5. And that's because we've removed this hydroxyl group at position 2, making it the 2-deoxyribofuranose. They are both D sugars because this carbon over here points up. So D2-deoxyribofuranose. And this hydroxyl group on the left points down. So that would be the alpha anomer. This hydroxyl group points up. And so this is the beta anomer, making alpha and beta D2-deoxyribofuranose. And again, this deoxyribofuranose is important because this makes up part of the backbone of DNA. And so now we'll look at fructose. Which is also a furanose. And so the basic name for this is fructofuranose. And they're D sugars because this carbon on the right points up. D-fructofuranose. And remember, we were looking at this hydroxyl group that's attached to this carbon, attached to this cyclic oxygen. We're not looking at this other carbon atom. And so this on the left has that shape, making it alpha. On the right, we have the boat shape, making it beta. So alpha and beta D-fructofuranose. And hopefully these examples have helped explain the nomenclature of pyranose versus furanose and alpha versus beta anomers.